A substation power transformer is designed to take an applied voltage and step it up for transmission over long distances, or step the voltage down for distribution to homes and businesses. The characteristic of a transformer that enables it to step up or step down voltage is the ratio of its primary windings to its secondary windings. If for any reason a winding is damaged, shorted, or isolated from the circuit, the transformer will not provide the desired output voltage. And in the case of winding damage or a short, continued use of the transformer could result in major transformer failure. To a degree, winding problems can be detected while they're still minor by a test known as the transformer turns ratio test. In this program, we're going to look at the purpose of turns ratio testing, the equipment used, how the test is performed, and what the results tell you. The purpose of a power transformer is to take a given voltage and change it to another specific voltage. It does this by inducing voltage from one winding to another physically separate winding. If there's something wrong with either winding, the transformer will not provide the voltage that's needed. At certain times, it's good practice to check the condition of a transformer's windings. A good way to do this is with a turns ratio test. In this part of the program, we're going to look at what turns ratio is, what can cause it to change, and why turns ratio is tested. First, what is a turns ratio? A transformer's turns ratio is the ratio of the number of turns in its primary winding to the number of turns in its secondary winding. For example, in this simplified illustration of a transformer, there are 24 turns in the primary winding and 6 turns in the secondary winding. This gives a turns ratio of 24:6. A turns ratio is usually stated in its lowest terms, so this turns ratio would be stated as 4:1. A transformer's turns ratio determines its voltage ratio. Voltage ratio is the ratio of the transformer's primary voltage to its secondary voltage. For example, with a 4:1 turns ratio, if 480 volts is applied to the primary winding, the voltage induced in and available from the secondary windings would be 120 volts. The voltage ratio, then, is 480 to 120. Stated in its lowest terms, the voltage ratio is 4:1. A transformer's voltage ratio is equal to its turns ratio. The turns ratio of a transformer can change for a variety of reasons. One cause is short-circuited winding turns. On a new transformer, winding turns may have been shorted during manufacture or during shipping to a substation. On an existing transformer, fault currents or other electrical or mechanical stresses can create shorts between turns. The turns ratio of a transformer can also be changed during maintenance. For example, on tap-changing transformers, if replacement parts for the tap changer are defective or incorrectly assembled, the turns ratio may be affected. So the turns ratio can be wrong in a new transformer that hasn't even been used. It can be wrong in a transformer that's been subjected to fault currents or other electrical or mechanical stresses. And it can be wrong in a transformer that's been modified or repaired in the field. If a power transformer is not operating at its designed turns ratio, it won't provide the desired output voltage. This can be critical to your customers. But consider this. If the turns ratio is incorrect because of an internal short circuit, that short circuit could escalate to a full-fledged transformer failure. So then, what's the purpose of a transformer turns ratio test? The purpose of transformer turns ratio testing is to check that the transformer is providing the desired ratio of primary to secondary voltage. Any improper ratio should be investigated to find and correct the problem. A transformer's turns ratio is typically tested using a portable turns ratio test set. In the next part of this program, we'll look at the principle of turns ratio testing and the basic components and operation of a turns ratio test set. But before going on to the next part of this tape, review the material in your text on the purpose of turns ratio testing and answer the questions provided. The test equipment that's typically used to test a power transformer's turns ratio is a standard portable turns ratio test set. In this part of the program, we're going to look at the principle of turns ratio testing. We'll also look at the components of a turns ratio test set and how the set works. We'll use this simplified illustration to describe the principle of turns ratio testing. This part of the illustration represents the power transformer to be tested. It includes a low voltage winding with terminals X2 and X1, and a high voltage winding with terminals H2 and H1. This part of the illustration represents a turns ratio test set. It includes a source of AC voltage, shown here as an AC generator coil and hand crank, a reference transformer with a low voltage winding, and a high voltage winding. The high voltage winding is tapped so that the turns ratio of the reference transformer can be adjusted. The test set also includes 3 meters. The left meter is an ammeter. It indicates the energizing current to the low voltage windings of both the power transformer and the reference transformer. The middle meter is a voltmeter, which indicates the generator's output voltage that's applied to the low voltage windings of both transformers. The right meter is a null detector. It indicates the magnitude and direction of current that results from voltage that's induced in the high voltage windings of both transformers. Also included in this illustration are test leads. One pair of the test leads, called the exciting leads, contains 2 conductors that are used to apply voltage from the generator across the low voltage winding of the power transformer. These same test leads contain another 2 conductors that are used to apply the generated voltage across the low voltage winding of the reference transformer. A second pair of test leads, called the high voltage leads, connect the high voltage winding of the power transformer with the high voltage winding of the reference transformer and with the null detector. In principle, here's how the transformer turns ratio test works. AC voltage is applied to the low voltage winding in both the power transformer and the reference transformer. Voltage is induced in the high voltage windings of both transformers. The voltage induced in the power transformer applies an electrical force in the direction from the H2 terminal to the null detector. The voltage that's induced in the reference transformer applies an electrical force in the opposite direction to the null detector. If the turns ratios of the 2 transformers are equal, the induced voltages will be the same. The voltages cancel each other out, and the null detector indicates no current flow through the circuit. If the turns ratios of the 2 transformers are not the same, the voltages from the 2 transformers will be different. If the ratios are such that the voltage is greater from the power transformer, that voltage will overcome the voltage from the reference transformer and cause current to flow in a given direction, as indicated by the null detector. If the voltage is greater from the reference transformer, that voltage will overcome the voltage from the power transformer, and the null detector will indicate current flow in the opposite direction. To determine the turns ratio of the power transformer, the turns ratio of the reference transformer is adjusted until the null meter indicates no current flow. The turns ratio setting of the reference transformer is noted. This is also the turns ratio of the power transformer. So, to perform a turns ratio test, voltage is applied to both a reference transformer and the power transformer. The turns ratio of the reference transformer is adjusted until a null detector indicates no current flow. Then the turns ratio setting of the reference transformer is noted, because that is also the turns ratio of the power transformer. Now, in looking at the principle of turns ratio testing, we've identified some of the components of the test set. Let's see what these and other components look like on an actual turns ratio test set. Here's a typical turns ratio test set. It may look a little different from the set you use, but it will have the same basic features. This particular test set has a hand crank that is turned to generate test voltage. This powers a generator inside the test set that provides the test voltage needed for the test. Also inside the test set is the reference transformer. The reference transformer is a tapped transformer with a precise turn count at each tap so that the transformer's turns ratio can be adjusted in controlled increments. The transformer taps are connected to 4 tap selector switches, which are adjusted at the panel of the test set by 4 dials. The left dial changes the turns ratio of the reference transformer in steps of 10 turns from 0 to 120. The next dial changes the turns ratio in steps of 1 turn from 0 to 9. The next dial changes the turns ratio in steps of tenths of a turn from 0 to 9/10. The fourth dial is a potentiometer, which provides a continuously variable voltage. This, in effect, allows changes in the turns ratio as small as 1/100th of a turn from 0 to 1/10 of a turn. Above each dial is an indicating window that displays the selected turns. Above the dials and indicating windows are 3 meters. The meter on the right is the null detector. The detector is connected so that when the ratio of the power transformer is greater than the selected ratio on the reference transformer, the needle will deflect to the left of center. When the ratios are the same, the needle will rest at null, which is center scale. And if the ratio of the power transformer is less than the selected ratio on the reference transformer, the needle will deflect to the right of center. The middle meter is a voltmeter, which indicates the voltage that's applied to the low voltage windings of the power transformer and the reference transformer. The desired test voltage is typically 8 volts. The meter on the left is a current meter. It indicates if the output current of the power source is flowing through the exciting leads of the test set to the low voltage windings of the transformers. As indicated earlier in the illustration, a turns ratio test set typically comes with 4 test leads. The 2 leads with clamps are the exciting leads. These leads are connected to the low voltage windings of the power transformer. The test voltage is applied through these leads to the low voltage windings of the power transformer and the reference transformer. The 2 leads with clips are the high voltage leads. They're connected to the high voltage windings of the 2 transformers. A final component that should be identified on the test set is a grounding terminal. The test set is typically connected to a station ground through this terminal to bleed off any voltages induced from other sources in the substation. The turns ratio test set that we looked at is typical of those used in the field. However, it's not the only type of turns ratio test set. There's a set that's designed to test 3 phases at one time. Other sets have digital readouts, are operated by batteries or AC power. Some even have a printer that prints out the test results. Despite their differences, the principles of operation and the functions of the components that we looked at are similar. Now, so far, we've looked at why turns ratio testing is needed, the principle of performing the test, and the equipment that's used to perform the test. In order to get usable test results, the test leads of the turns ratio test set must be properly connected to the transformer. In the next part of this program, we'll look at the test connections that are required to make a complete turns ratio test of a typical substation power transformer. Be sure to review the material in your text on test equipment before continuing. Typically, the turns ratio for a substation power transformer is tested 1 phase at a time. So a 3-phase power transformer requires at least 3 turns ratio tests. If the windings of all power transformers were arranged the same way, you'd only have to learn where to make the connections for the 3 tests. But the windings are not all arranged the same. There are delta Y arrangements, Y-Y arrangements, Y-delta arrangements, and others. The test connections for each are slightly different, but the principles for making the connections are the same. In this part of the program, we're going to look at the principles for determining where to make the test connections to test the turns ratio of a given transformer. The transformer example that we'll use is a delta Y power transformer. The key to determining where to make test connections for a turns ratio test is on the nameplates of the power transformer. The nameplate contains a connection diagram for the windings of the transformer. This symbol shows that the higher voltage windings are delta connected. Each letter number designation represents a higher voltage terminal. Each line in the symbol represents one phase winding of the transformer's higher voltage windings. For example, the line connecting H1 and H2 represents one phase winding of the higher voltage windings. The line connecting H2 and H3 represents another phase winding of the higher voltage windings. And the line connecting H3 and H1 represents the third phase winding. This symbol shows that the lower voltage windings are Y-connected. Each letter number designation represents a lower voltage terminal, and each line represents one phase winding of the lower voltage windings. These lines include X1 to XO, X2 to XO, and X3 to XO. The lines on both symbols that are parallel to each other represent the windings that are of the same phase. For example, the higher voltage winding, represented by the line H1 to H3, is the same phase as the lower voltage winding, represented by the parallel line X1 to XO. When test connections are made, the exciting leads of the turns ratio test set are connected to the terminals of one of the lower voltage windings. For an example of the connection, the exciting leads are connected to the terminals X1 and XO. The high voltage leads of the test set are connected to the same phase winding terminals of the higher voltage windings. In this case, the high voltage leads are connected to the terminals H1 and H3. Another point to note when making connections for a turns ratio test is that of the test leads, the end of one exciting lead and one high voltage lead is red. The end of the other exciting lead and high voltage lead is black. The red leads are connected to the higher and lower voltage winding terminals that are at the same ends of the lines on the nameplate connection diagram. For example, the red exciting lead would be connected to terminal X1, and the red high voltage lead would be connected to terminal H1. The black exciting and high voltage leads are connected to the XO and H3 terminals respectively. To test the turns ratio of a second winding of the transformer, the red test leads may be moved to the X2 and H2 terminals, and the black leads are connected to the XO and H1 terminals respectively. The third winding test connections, then, would be the red leads to the X3 and H3 terminals and the black leads to the XO and H2 terminals. So, the connection diagram on the transformer nameplate helps you identify which terminals to connect the test leads to for a turns ratio test. Now, another diagram on the transformer nameplate, the bushing layout diagram, helps you determine which terminal is which on the transformer. These circles represent the three high voltage bushings and terminals H1, H2, and H3. These circles represent the four low voltage bushings and terminals XO, X1, X2, and X3. The first set of test connections that we looked at using the connection diagram was to the X1, XO, H1, and H3 terminals. Here are the connections as they would be made to the terminals on top of the transformer. The principles that we looked at for making test connections for a turns ratio test apply to most substation transformers. These principles included connecting the exciting test leads to the terminals of one winding of the lower voltage transformer windings, connecting the high voltage leads to the same phase winding terminals of the higher voltage windings, and making sure that the red test leads are connected to corresponding low and high voltage terminals. We also saw that the connection and bushing layout diagrams on a transformer's nameplate are very helpful in determining precisely where to make the connections for a turns ratio test. So far, we've looked at the purpose of turns ratio testing, the principle of performing the test, the equipment used, and where to make the test connections. In the next part of this program, we'll look at general procedures for performing the test. Remember to review the material in your text on test connections before continuing with this tape. In order to get useful, reliable test information, a turns ratio test has to be performed properly. This means that the transformer must be made safe to work on. The test leads must be connected to the right terminals, the test set must be properly operated, and the results must be accurately documented. We've already looked at where test connections are made. So in this part of the program, we're going to concentrate on taking the proper safety precautions and operating the test set. One of the first safety precautions that you should take is to make sure that the transformer is de-energized. If you're responsible for taking the transformer out of service, be sure to follow your company's procedures. If the transformer has already been taken out of service for you, you need to verify that it's been disconnected from the load and all normal sources of energy, that it's been visibly separated from the source and load circuits, and that it's been grounded. The grounds are kept on until just before the test is performed. It's also a good practice to ensure that control and power supply circuits to auxiliary devices on the transformer are opened and tagged. Another safety precaution is to restrict access to the work area, usually by placing barriers, ropes, or warning signs around the work area. Once the transformer has been made safe to work on and the area is secured, specific preparations for testing can be made. For example, the grounds are removed from the transformer just before the turns ratio test is performed. This is typically done by lifting the conductors from the transformer terminals with the ground still attached to the conductors. However, if there's energized high-voltage equipment nearby that may induce voltage in the transformer windings, it may be necessary to keep a ground on one end of the high-voltage winding and on one end of the low-voltage winding that are being tested. All other grounds would be removed. Next, the test leads are connected to the appropriate terminals on the power transformer. As a safety precaution, the turns ratio test set is grounded by applying a ground from the ground terminal on the instrument panel to a station ground. Also notice that the worker is wearing rubber gloves. It's considered a good safety precaution to wear rubber gloves, not only when making the test connections, but also when operating the turns ratio test set. Yet another important safety precaution is to make sure that all personnel stay clear of all exposed connections and conductors when the test set is being operated. Once the test leads are properly connected, the test set dials are set at 01.000. Then the generator is slowly cranked. If the null meter deflects to the left, the test leads are correctly connected to the transformer and the test can continue. If the null meter deflects to the right, the test lead connections are incorrect and need to be checked. If the test leads are properly connected, the next step of the test is balancing. Balancing is adjusting the turns ratio of the reference transformer until it balances with or is the same as the turns ratio of the power transformer. When balancing is completed, the settings on the test set indicate the ratio of the power transformer. To balance, the generator is cranked while observing the null detector. If the needle deflects left, the dial's turned clockwise one step while continuing to crank the generator. This is repeated until the needle deflects to the right of null. When the null detector needle deflects right, the dial is turned back or counterclockwise one step. The process is repeated with the second dial. The dial's turned clockwise one step at a time while cranking the generator until the null detector needle deflects right. Then the dial is turned back one step. The process is repeated once more with the third dial. To adjust the fourth dial, the generator is cranked slowly and continuously while the dial is slowly turned clockwise. As the null detector needle deflection gets smaller, the generator is cranked faster until the voltmeter reads 8 volts. The dial is adjusted more until the null detector needle rests over the null mark in the center of the scale. At this point, the ratio of the reference transformer is balanced with the ratio of the power transformer. The dial numbers are copied in sequence on the test form provided by your company for documenting turns ratio test results. This number over 1 is the turns ratio for the windings being tested on the power transformer. If the power transformer that you're testing is a tap-changing transformer, the test is repeated at different tap settings without changing the test connections. Depending on your company's procedures, you may be required to test the turns ratio at every tap position or at several specific tap positions. Then, when you finish testing one phase of the transformer, the test leads are moved to the next phase and the test procedures are repeated until all three phases have been tested. Now, in this part of the program, we looked at safety precautions and procedures for turns ratio testing. The final aspect of turns ratio testing is evaluating the test results. We'll look at what various turns ratio test results tell us in the next part of the program. There are two common problems that you can have when performing a turns ratio test. One is an inability to get the test set to balance, and the other is getting a turns ratio that's not what it's supposed to be. In this last part of the program, we're going to look at various results that you can get from a turns ratio test and what they tell you about the transformer. Sometimes when performing a turns ratio test, you may not be able to get the test set to balance. Generally, an inability to balance indicates either a short circuit or an open circuit in the windings being tested. The response of the meters on the test set will give you a clue as to whether the problem is a short or an open. If the current meter indicates high current, while the voltmeter indicates low or no voltage, this generally indicates a short circuit in the windings being tested. On the other hand, if the current meter indicates normal current and the voltmeter indicates normal voltage, but the null meter shows no deflection regardless of the ratio selected, the problem is most likely an open circuit in the high voltage windings of the power transformer, or the high voltage test leads aren't securely connected. If there's a short or an open in the transformer windings, the problem will have to be located and corrected before the transformer can be put back into service. This is because a short or an open can lead to a major transformer failure. But before you report that you couldn't get a balance, it's a good idea to check your work. Make sure that all your test leads are securely connected to the proper terminals and that you performed the test properly. Now suppose that you had no problems doing the test and you documented a ratio for each phase of the transformer. What do those ratios tell you? By themselves, nothing. They have to be compared to the ratios that the transformer is expected to provide. The expected ratios can be calculated from information on the transformer's nameplate. The information needed is the winding voltage rating for both the high voltage and low voltage windings. To calculate the expected turns ratio, the high voltage rating is divided by the low voltage rating. The voltages used depend on whether the windings are Y or delta connected and the position of the tap changer, if the transformer has a tap changer. If the windings are delta connected, only one voltage is identified on the nameplate. For example, here, the high voltage windings are delta connected and the voltage rating is 113,000 volts. This figure goes in the high voltage rating part of the turns ratio formula. If the windings are Y connected, two voltages may be identified on the nameplate. For example, here, the low voltage windings are Y connected and two voltages are listed. The larger Y voltage is the phase-to-phase system voltage. The smaller Y voltage is the phase-to-ground winding voltage. The winding voltage is the voltage that's used in the calculation. This figure goes in the low voltage rating spot of the turns ratio formula. Dividing the high voltage rating by the low voltage rating works out to 7.476, which is the same as saying 7.476 to 1. So the reading that you'd expect to get on the turns ratio test set for this transformer is 7.476. Now, if the transformer has a tap changer, it will have a different voltage rating for each tap setting. For example, this transformer has a no-load tap changer on its high voltage windings. The nameplate lists a high voltage rating for each of the 5 no-load tap positions. By looking at the no-load tap changer handle, we can see that it's set at tap position 3. Generally, the turns ratio test is made with the no-load tap changer at its given position. Turns ratio is not checked for other tap positions. For this transformer, the high voltage winding rating at tap 3 is 113,000 volts. This is the high voltage figure that's used in the turns ratio formula. Here's a transformer that has a load tap changer on its high voltage windings. The turns ratio is calculated for each load tap changer position that the transformer is tested at. For example, the voltage on the high voltage winding with the tap changer at the neutral tap setting is 220,000 volts. This is the high voltage figure that's used in the turns ratio formula for calculating the turns ratio at the neutral tap position. At the full raise tap setting, the high voltage figure that would be used in the formula is 242,000 volts. And at the full lower tap setting, the high voltage figure that would be used in the turns ratio formula is 198,000 volts. As indicated on the nameplate, the low voltage winding rating is 36,000 volts. This is the low voltage figure that would be used for this transformer in the turns ratio formula. The ratio that you get on the turns ratio test set is compared with the calculated expected ratio. Depending on your company requirements, a difference of anywhere from plus or minus 1/4% to plus or minus 1% may be acceptable. Be sure you know your company's maximum acceptable difference. Now, in the example that we looked at, the calculated ratio was 7.476. The ratio that we got on the turns ratio test set was 7.470. This is a difference of less than 1/10%. If our maximum acceptable difference is 1/4%, the transformer turns ratio tests out okay. If the ratio was not acceptable, this would indicate that there's a problem inside the transformer. It could be a short, an open, loose contacts in the tap changer, defective or incorrectly assembled tap changer parts, or a number of other problems. In any event, the problem would have to be located and corrected before the transformer could be put back into service. Now, in this program, we looked at the purpose of turns ratio testing, the equipment used to perform the test, where the test connections are made, common safety precautions and test procedures, and what the test results tell you. It's important that you understand why you test turns ratio, how to safely and accurately perform the test, and what various results mean. Then you can be fairly certain that the turns ratio tests that you perform will help prevent costly transformer failures.